last class, sir started SVM. So we'll try to complete all the possible variations, like all the possible related things to SVM today. If not, we'll discuss on Thursday. So just a bit of warning, like it might be a little bit math heavy, but stop me in between if you don't understand anything. So like don't stay silent, ask doubts. Okay. I'll use the board also if you want. Yeah. So as last class you saw, so why we're learning, like why we're now discussing about SVM. So we want to learn a classification model. So SVM is one of the classification model, and when we say classification model, so we have different types of data, right? We have data that are lying on a single line or a 2D plane or a like kind of 3D plane or more than three-dimensional plane also. Like if all the points are one-dimensional, we know the kind of separator can be a point. If all the points are like two-dimensional, separator can be line. So it is easy to visualize, right? So if you see these things, so I'll draw for 2D. Yeah, so let's say this is like a point for one class and these are point for another class. Right, so this is just a line that can separate these two classes very cleanly. Similarly, you can visualize for a plane three-dimensional data points and higher dimensional data points. The terminology for higher dimensional data point classifier is a hyperplane. So what does SVM do? So the general intuition behind SVM is okay. So I'll start with this intuition, but we'll discuss in detail what are the other possibilities. So we have two classes here. Let's say this is class one, this is class two, right? So what we'll take? We'll take 2 points or any point that is closest to like any 2 points from two classes that are closest to each other. So what do we mean by closest to each other? So we'll discuss. So if we figure out 2 points that are closest to each other from two classes, two opposite classes, then we'll just need to find a dissecting line. That is the like intuition behind this hyperplane by SVM. Um, but the point is like, so we're saying this is the solution of SVM. But if we try to find kind of a linear classifier, we can find many linear classifier. This can be linear classifier also. But SVM says this is the optimal classifier. Why that is the optimal classifier? We'll discuss. Yeah. So this is the goal as discussed earlier. So how do we represent this hyperplane? So we are saying this is the hyperplane. So we are saying this is the hyperplane. So how do we represent this hyperplane? So representing this is a line, right? So let's discuss about 2D only, then we can generalize it to any n-dimensional space. So this is a line. So what is the general equation of a line? We know from our elementary mathematics, so y equal to mx plus c, right? So this is what we know from elementary mathematics. But if we kind of generalize into higher dimensional space, so it will be like kind of W transpose x plus b. So b is the bias term. This W is the what this W is. That is pretty much important. What this W do and how do we visualize this W? So if this is the line, the W is a perpendicular vector to it. So that's the W. So what W does, it kind of fixate the orientation of this line. So if W changes a little bit here, the line will be like this, because this W is a perpendicular axis to this whatever the separating hyperplane. What this B does, what this is generally called the bias. This is weight. This is bias, right? So what this bias does. So let's imagine another scenario. So I think this is visible. I'll just this is -1, this is +1, this is +2, +1, +2, -1, -2. So if I'll say this, there is a line x plus y equal to 0. So what is the bias term here? Bias term here is 0. So meaning it is passing through origin. If I say there is a line x plus y equal to 1, the bias term is 1. So what it does, the bias term, this bias term will shift this line above, that will pass through this +1 on y-axis, +1 on x-axis. This is the importance of B. So B just shifts this line like towards this way or towards this way, but the orientation, the angle of the line will be decided by the W. Okay. So this is the kind of the representation of the hyperplane. So now how do we visualize these two class points? Like now we are using this kind of hyperplane to classify these two classes, right? So one side of this, you can easily see one side of this hyperplane represents one class, other side is another class. Right now we need a mathematical formulation to kind of say that. So the mathematical way is like if wx plus b is greater than 0, it's one class. Wx plus b less than 0 is another class. Why it happens, we'll see in the next slide. And any point on that particular hyperplane, it will be wx plus b equal to 0. That will satisfy that equation. So let's kind of observe this diagram properly. Yeah, so if you observe this line 2, let's say this is one hyperplane and line 1 is another hyperplane. Okay, so again I'm repeating, so stop me if you have any doubt. Okay. So there is a point, let's say 2 comma 1.5. So now we will decide whether this 2 comma 1.5 point will be on the positive side of line 2 or on the negative side, similarly for line 1. So how we'll decide? We'll put this point on this equation, equation of the line 2, again same point on the equation of line 1. So if you put that point on the equation of line 2, you will get 0.5, that is greater than 0, meaning that is on the positive side of the line. If this is the hyperplane, you can say this is the positive side of the hyperplane. Similarly, if you put that similar point on the line 1 equation, you will get minus 0.5. So you can say like this point is on the negative side. That's how we'll decide whether the point is on the positive side of the classifier or the negative side of the classifier. So I'll use classifier and the hyperplane interchangeably. So now coming to SVM training. So what we decided for SVM? Okay, so I gave you the original intuition. So we have to find a support vector. Yeah, so we have to find a support vector that will dissect this kind of two closest point, the closest point from the opposite classes. So if I have not given you this intuition. So these are the two data points that is given to you. I want to find out a classifier. So what are the general idea? How do you do it? Any guesses? So SVM solution is not the answer. Any other answers I'm expecting? So you are given data points from two classes. You want to find a classifier. Anybody? So if I suggest one approach, find the mean of this class data points and find the mean of these data points. Let's say mean is here for this class, mean is here for this class. You kind of dissect these two kind of mean of these two classes. What will be the problem there? Any answers? If I try to find the classifier by dissecting the mean of these two classes. So generally, I have drawn the points in a way that it is looking very nice, but in real world, the data points can be very noisy. Let's say there is a point from this class 2 that is lying here, kind of outlier. So the mean will shift towards here. Then classifier will look like this. This is not optimal one actually, right? So there are many demerits. So we can discuss about other classifiers like this and point out to their demerits. So to kind of get rid of all the kind of noisy scenarios, the SVM formulation tells you just consider these two closest points. They're called the support vectors. This is the support vector. This is the support vector for this class. Just consider these two closest point and try to dissect it. So that's why the SVM is robust as compared to other algorithms. So now, if we say this is the support vector, now this is the support vector, how do we represent these support vectors? Right, so these are the line passing through these points. How do we represent the support vectors? So general formulation in SVM is you represent this by again some W transpose x plus b equal to +1 for the positive class. Same here, it goes W transpose x plus b equal to -1 for negative class. So it +1 -1 you can change. So one class is positive, one class is negative. So it's just representation. So why +1 and -1? Why not some other value? So why fix it to +1 or -1? So if we, instead of use +1 or -1, if we use plus k, let's say some generic number, so that will not change anything, not a single point about the SVM formulation, SVM solution will get. So we'll see towards the end of the class today. So this will not change anything, but having +1 helps us in the optimization step little bit to solve all the kind of optimization problems. Okay, so this is the formulation. So we'll have a separating hyperplane, and the support vectors will be the line passing through these closest points on two opposite classes. And the representation will be double transpose x plus b equal to 0 or equal to -1. So again, another little bit. So I'll update the slides. So the W0 and B, I'm representing them interchangeably. So the meaning of W0 and B are same. They are the bias terms. Okay, so this is about the SVM training setup. So you are given data points xi and yi, xi, comma yi. Yi is either +1 or -1. Xi is the data point. So it may be a two-dimensional data point, three-dimensional data point, some d-dimensional data point, and yi is just the label +1 or -1. So now, if so, we have this. I'll just read this. So I think everybody understood why this equation is just +1 -1. Now we need to go a little bit deeper to find this particular W and B. So which is the hyperplane? What is the equation of the hyperplane that will give us the uh, optimal classifier, right? So this is the line. So according to our intuition, this is the line. So this is the, let's say, support vector. So if my drawing is maybe not very accurate, but just consider this is the support vector. These are the two support vectors, and this is the separating hyperplane. Now, so we know the W direction is this. W direction is this, right? So, so when we say there's the closest point between two classes, so what do we mean exactly? The perpendicular distance between any two points. So it might happen that there is a point here, that is the support vector. There is a point here, that is the support vector. So, but that doesn't mean this is the distance between closest point. The distance between closest point is you project this point and project this point to this perpendicular axis. First project them onto the perpendicular axis, then find the distance. That is the perpendicular distance between these two points. That is the notion of kind of finding the distance between support vectors. So that's what we'll do. If you see the margin equation, how we have represented margin, d equal to W transpose x2 is, let's say, from one class, x1 is from other class, x2 minus x1 by norm of W. So we have to divide by the normalization factor. So if you multiply W transpose into x2, so whatever the point on the x2 class, it will get projected onto W. Then you multiply, it will be unroll into W transpose x2 minus W transpose x1 by norm of W. Right? So this will give us this point, and this will give us this point. Now you find the distance, right? So the idea is you have to kind of maximize this margin. So, but if you see this distance now we computed between these 2 points, that is parallel to W also. So we use that idea to find what is the optimal W. So the by definition, x2 minus x1 is parallel to W, meaning it's some lambda multiplication of W. And we know for x1 classes it is -1, x2 classes it is +1. Then if you subtract these two equations, it will give us W transpose x2 minus x1 equal to 2. Right? Then we know also this concept, this W x2 minus x1 is parallel to W. Now if you replace all the mathematics, so what we figured out, one equation we got is W transpose x2 minus x1 is equal to 2. This is one equation we got. Another equation is x2 minus x1 is equal to lambda into W, right? So now if you put yeah, So now if you put x2 minus x1 equal to lambda into w in that equation, what you will get? Lambda equal to 2 by w transpose w, right? So you just put this value here, right? You will get lambda equal to 2 by w transpose w. Now we have to find this margin width, like what will be the exact distance. So we represented this way, but we never found the exact distance between that. So how do we find the exact distance if this is the line? And so what is the distance? Let's say we represented by d. If this is the d, what will be the d mod? D mod will be x2 minus x1 transpose x2 minus x1. This is just basic vector algebra. So how to find the length of a vector? So I'm not discussing in detail about that. So how do we find the length of a vector? This is d transpose d square root over, right? So that's what we did. So if you replace all those possible values, so what you will get? This is 4 by w transpose in w transpose w. So we're only concerned about the relations. So the constants we'll get in the constant optimization problem. So what we got here? So the width here is some multiplication of 1 inverse w transpose w. The margin width we got d is the length of d actually is inversely proportional to 1 by w transpose w. This is what we got. So what we have to do, particularly this, we have to maximize this gap. If we maximize this gap, we are pretty sure that this classification will be very correct, right? So why this classification will be correct if we are maximizing this class? If support vectors are far from each other during test time, what happens? There will be less in less chance for error. So I'll come to test scenario, then I'll explain why there is a less chance of error if the distance is maximized. Yes. X2 minus x1 is parallel to. Yeah, so as I explained, so first this x2 minus x1, what we need to figure out how are these s2 and minus x1, x2 and x1 we are visualizing, they're closest to each other. So the notion of closeness, we are not computing by this distance, we are computing by vertical distance. So vertical distance in the sense you project these 2 points onto the w first. So then if you project onto a w, then this x2 minus x1 itself is a vector like this. So that's why it's parallel to W. W is always already perpendicular to this hyperplane. Okay. Any other doubt till now? Yeah. Yes, you are choosing such W so that it is parallel to x2 minus x1 for those close x2 and x1. Again, we are choosing those x2 and x1 which are very close enough on the vertical distance. So you imagine some W. Let's say if I choose this W, okay. So that intuition I'll give you here. Again, another set of points. I'll just draw the support vectors, possible support vectors. This is, let's say, support vector. This is, let's say, support vector. This is okay. So visually, if we see here, it looks like this should be support vector, right? This and this should be support vector. So if these two should be a support vector, the kind of vectors passing through them will look like this. Now, if I decide, let's say, not this and so if this is not the W, optimal W, if I decide this is the optimal W, okay, imagine this scenario. So what will happen? This distance is, let's say, this is some distance D1, and this is some distance D2. So if you do little bit of math, so what it will come out? D2 will be D1 cos theta. So in that way, if you can prove that D2 is always less than D1, right? So that's why you have to always take this perpendicular distance and dissecting will be the W. So this is the intuition. Again, the optimization problem will automatically figure out those things. No, these are the 2 points. I'm just saying instead of this W, if I have taken this W. So you can take any 2 points. any two points between which the distance is minimum. Huh? Pardon? Yeah. Any form of distance you can take. Any form of distance actually. It's not just Euler distance. Any distance you can take. Okay, so you can choose any pair of points. You choose those two that pair particularly where the distance is minimum for a particular W. That W will figure it out. Optimization algorithm. So I am just explaining here, instead of this W, if I take this W, what is the problem? So this D2 will not be the maximum margin. So that what will happen? Okay, this can be for this training data point. Maybe this will classify these two classes correctly. But when test data point comes, maybe there is a point here. So that is corresponding to class 1, but because of this classifier, it will assign to class 2. That's a wrong classification. But this W will correctly classify. So that's why we need the maximum margin. Okay, so this is not in the slide. You can note it down. Yeah. So what we are discussing? So we have to maximize this D. So D is inversely proportional to W transpose W. So you have to maximize D, meaning, so generally maximization problem is a little bit tougher, but a minimization problem in the constant optimization is easier. So what we do? We minimize, instead of maximizing D, we'll minimize D. So if you minimize D, so what will be the problem? Now updated optimization problem, minimize W transpose W, right? So this is the term we have to minimize. But for again a mathematical convenience, we just divide by 2, because W transpose W, when you kind of differentiate, there will be a square term, also 2 will come outside. So for mathematical convenience, what we did, we try to minimize this term. But there are some constants. Constant in the sense, all these data points should be correctly classified. So because of that constant, this closest points will automatically get selected by the optimization algorithm. Right. So what are the constants? So for the positive class, it will be all these points should be W transpose X plus B for positive class should be greater than equal to 1 for positive class. For negative class, W transpose X plus B will be less than equal to -1 for negative. So now this is our Y value, right? So if what will happen if we multiply Y to this equation altogether? So if I multiply that to Y to this equation, it will be Y into W transpose X plus B, right? So for positive class, anyway Y is positive, W transpose X plus B is positive, so it will be greater than 0, X is greater than +1. For negative class, Y is negative, W transpose X plus B less than -1, less than equal to -1. So this minus multiplication again will be greater than equal to 1. So that is the single constant we will use instead of two constants. So this this is the so these individual constants I have not written on the slide. You can update it. Individually, these are the two constants. For positive class, W transpose X plus B is greater than equal to 1. Negative class, W transpose X plus B is less than equal to -1. If you combine like multiply Y here, so the combined constant will be this. So this is something called the hard margin problem. Why it is called hard margin problem? So you are fixating the margin based on these closest points. But again, this is a very much linearly separable data. This is a very nice scenario. It's easy to solve. But there are scenarios where again one scenario gave you where there is an outlier point here. Let's say not this one. Let's say outlier point here for this class 1 itself. Another scenario is let's say there is a single point here that is X of this class, but it is lying here. But if you consider this is the closest distance, like these two are the closest points, then what will happen? Because we know this is visually looking like outlier, and we know actually this is outlier point. But if we run the hard margin classifier, it will choose these 2 points, and the hyperplane will be this. Let's say. Then what will happen during test time? There is a point here that should be, let's say, for class 1, that will wrongly classified for class 2. Okay, so for that reason we need something more than just the hard margin classifier to take care of these outliers and these outliers. We have two types of outlier now. Yeah. Oh, it's just very much linear classifier, then hard margin will give us correct answer every time, any dimension. So if there are outliers like this or outliers like this, hard margin classifier will not give correct answer to us. Okay, there will be error during the test set and testing scenario. So to counter, like kind of take care of these two kinds of outliers, so note it down, there are two kinds of outlier. There is outlier in the same class that is lying very far, and the outlier in the same class that is very much close to this kind of separating hyperplane. So that gives false impression that this is a support vector. This is actually not a support vector. This gives us false impression that this is a support vector, right? So now through something called soft margin classifier, we'll take care of these both scenarios. So let's discuss how we'll take care of both the scenarios. Any doubt till now? Yeah. Mm-hmm. Yeah. So if many points like if this is close to margin, but other points are also concentrated around it, then it can be support vector. But visually, it looks like it's an outlier actually, right? The data points are here, they're concentrated here. There is a single point here. So that's the definition of outlier. Like it's far away from the central concentrated data. Right. So there are algorithms that will give you idea how to compute the outlier. So that's beyond this lecture's attention. So we are not discussing that, but you know the general definition of outlier. So this point visually looks like an outlier. So how do you handle this scenario? That's the goal of soft margin classifier. How will compute this outlier? We can discuss later. Yeah. So what we'll do? We'll introduce something called slack variable. So what is a slack variable? Slack variable is a variable that is assigned. It's kind of a random variable that is assigned to every data point in the training data set. Okay. So what it does, if something is outlier of this nature or outlier of this nature, it will try to penalize it. So if you will try to penalize it, how will penalize it? So there is another kind of outlier also. Let's say there is a point of class 1 that is lying here and class 2 lying here, right? So this is also there are four kinds of this you can club into one kind maybe. This is outlier of type 3. This is outlier of type 1. This is outlier of type 2. Okay, these are majorly three kinds of outlier points we'll see in classification scenario. Okay, so now what happens? So if this is the hyperplane we know. Okay, so given data, we can easily figure it out. Okay, this is the majorly concentrated data for class 1. This is the majorly concentrated data for class 2. We can ignore all these outliers. This will be the hyperplane. Now we have to take care of these outlier points. So the intuition is if you take care of, so you generally ignore this outlier because this is very far from the centrally concentrated data, and support vector only consider the closest point. So you just ignore this. Okay, so you ignore this point. Now these two scenarios are there. So this scenario, if you remember the perceptual learning algorithm, so this kind of data points will kind of tilt the hyperplane, right? Because of the error in the perceptual learning algorithm, it will become negative. It will kind of add it to the hyperplane. Then it will kind of fluctuate here and there. So now we have to take care of these outlier points first. So how we'll take care of these outlier points? Let's add some assign some slack variable to it. So if you assign some slack variable, now what we are saying about this? So we know this line is W transpose X plus B equal to plus 1. Right? This is plus 1, this is minus 1. So now what you do, so what is the value that is, what is the point that is outlier for this class? This is the point. So bring it back to this class. Bring it back to original class and bring this point back to its original class. So how do you bring it back to the original class? Subtract some variable called xi. So this xi variable is assigned to every data point. So only it will be non-zero if there is some outlier. For the correctly placed points, the xi will be 0. Okay. So if there is some outlier points, for those outlier points only xi will be some non-zero value. So that non-zero value, what it will do? It will To algorithm, it will say that, okay, I'm bringing back this point to this original class. Now you do the computation considering this is the margin. Okay, so this is what we'll do. Now, the point is, okay, so I add some point here. Okay, so what is the constant optimization problem? Earlier we saw what is the constant optimization problem. This is W transpose W. We have to minimize this W transpose W. Then under constant y into whatever is greater than equal to plus one. Okay, this was our constant optimization problem in the hard margin classifier. Now our kind of decision boundary is changed here. So W transpose X plus B is for this kind of points, it will be greater than equal to, for class 1, it will be greater than equal to 1 minus xi. For class 2, it will be less than equal to 1 minus xi. Sorry, minus 1 minus xi. Right? Now this xi new term has been introduced, right? So how do we optimize the complete scenario? So we have W earlier, B, and now this new term xi. Okay. So to optimize this, there is one nice formulation. So you have to add this xi to the minimization problem itself. So why we add this to the minimization problem? Let's say we don't add this to minimization problem. This is a distance, so this the minimum requirement is this has to be greater than 0. Xi has to be greater than equal to 0. This is the, because this is a distance parameter. This is distance variable or distance parameter. So this is the minimum requirement. So now if you don't add the extra optimization to the extra variable corresponding to xi in the minimization problem, what will happen? So it might so happen. So what you are doing? You are saying minimum value of xi is 0. If xi becomes infinite? If xi becomes infinite, this term 1 minus infinite will be negative infinite. All the points will satisfy that, and this will be this we can ignore completely. So what will happen? So the overall formulation will be y into W transpose X plus B greater than equal to 1. This is what we decided earlier, right? This is our constant. So if you are not restricting xi, so what will happen? This is y into W transpose X plus B greater than equal to 1 minus xi. So this will be minus infinity. If it is minus infinity, every point will like satisfy that constant. So that's a very loose condition, and it will not give us any optimal W. So it will say that you take any W, I will classify correctly. That's a wrong interpretation, right? So we have to put some restriction on xi. So to put some restriction on xi, we added that to the minimization problem itself. So we have to minimize, you have to constant the xi under the constant that this happens. It cannot grow very like kind of in uncontrolled way. So it can grow because this is a distance parameter, it can grow, but in a controlled way that the overall objective is minimized. Overall objective will be what now? So that is written on the slide. So minimization of W transpose W by 2 plus C, I will talk about it, C into summation of xi. The summation of xi has to be minimized such that this criteria satisfies y into W transpose X plus B greater than equal to 1 minus xi. Any doubt here? Any doubt? Why we are putting this xi in the minimization problem? Forget about C, I'll discuss about it. Yeah. Which one? I is total number of data points. Capital N. I correspond to each data point, capital N is the total number of. How do we know if a particular, that the algorithm will decide? You are not mentioning anything explicitly. This is the xi value for this particular point. So you are assigning a random variable to every point. Algorithm will decide, okay, which is the outlier, how much kind of weightage, how much of kind of penalization I have to do for every data point. That algorithm will decide. Any other doubt? Okay. So now let's come to see what is this C. So if you like kind of visualize this minimization a little bit closely, so we have to minimize both terms like W transpose W by 2 and this xi term. So what happens if C will grow very large. If C, because the overall goal is to minimize this, if C grows very large, algorithm will automatically force JIA to be very small value. So when C will be large, so if the JIA are very small, JIA are like this. So for that, those kind of data points, we can assign C to be very large. But if JIA is actually very large, let's say JIA is, let's say this is the data point for which we have assigned some JIA, and this JIA is really large. This is like very far from, or let's say there is another point here. This is really far. For this kind of data points, because there are some data points where JIA is very high, for that we have to keep the value of C less so that the overall minimization problem objective will be achieved, right? So that's what it says. If we have low C, and this means we have very high JI, and this can allow for large outliers. So in kind of lab sessions, you will be given data points like this, which have very large outliers. You can play around with different C value and see and visualize key having low C value will help us to get an optimal classifier in those scenarios where we have large outliers. Right, so we already discussed what happens if we remove JA, because it can go to infinity value, and this will not achieve our optimization goal. Okay, so again, now coming to, so how we have in hard margin we have two parameters to optimize for, W and B. In soft margin, three parameters, W, B, and J. So how do we solve this optimization problem? So this requires a little bit of math concept related to Lagrangian variable. So anybody comfortable with Lagrangian variable? Who knows Lagrangian variable? What is a Lagrangian variable? How do we convert a function to Lagrangian? Okay. So I'll give it a quick intro. I'll not go very deep into it. So in Teams, maybe I'll refer to some lecture notes that you can go through to understand the Lagrangian variable. Because if I'll go over Lagrangian, that will take a whole single class. Yeah. During training. I'll come to testing scenario. Don't worry. So that's a separate slide. So just think about the training. So how will get this optimal W? So that's now our only goal. How will get this optimal W? What will happen in during testing? We'll see. So all the parameters we're discussing, they're only valid for the training scenario. So now coming to something called Lagrangian variable. Again, I'll discuss in a very shallow way. So how much time I have? Yeah. So I'll discuss in just quickly 2 minutes, but I'll refer to some slides. If there is some doubt, we can discuss maybe in some extra sessions, because there are so many things to cover. We cannot afford a single class on Lagrangian. Okay. So what is Lagrangian? So anybody knows convex set? What is convex function? What is convex set? No prior on convex function, convex set. Okay. Okay, then definitely whatever the PDF or whatever the slides I'll share, just go through it to understand the basic nitty-gritties. The intuition is, let's say there is a function that is given to us to minimize f of x. Let's say this is the function we're trying to minimize, but for some reason, minimizing this f of x is infeasible. What do you mean by infeasible? The dimension is very high, or the number of data points can be very high. So because of computational efficiency, this is infeasible. There are some scenarios, not just because of computational efficiency, because of some mathematical formulation also. Sometimes this kind of minimizing this f of x becomes infeasible. So this is when this is given to us. This is called a primal solution. Primal solution, right? So if we so there is a scientist Lagrangian, he came up with something called, if we convert this minimization problem to kind of max-min problem. So what max-min over what on what, that is different scenario of some other variable. So now there is, so the problem was it was infeasible because of x. Now we removed x from the parameter itself. You transform x in a such a way that now this function is of some g of alpha, and solving this g of alpha is feasible, right? So converting from this infeasible solution to a feasible solution, this is the goal of Lagrangian. So this is called the primal formulation. This is called dual formulation. So how do I do it? So, so the intuition, basic intuition again from your elementary mathematics, because we cannot afford a very long discussion on it. So if I give you if I give you solve this equation 2x plus 3y equal to 4, x comma y greater than equal to 0. Let's say another constant is x square plus y square equal to 4. So this is another constant. Let's. So these are two constants. So sorry, not 4. So you have to minimize 2x plus 3y. This is the minimization objective. So and this is the constant. So this is one way you can like kind of okay. So you know x square plus y square equal to 4, meaning so x plus y x y values you know. So this is a circle. Maybe it's very small to see. So x square plus y square equal to 4 is this is a circle, you know, right? And 2x plus 3y will be a line, right? So you know, so whenever it will intersect, whichever point it will intersect on this side, this will be the minimum point, right? Visually, you know this. So how do we find the minima? So this is the elementary mathematics. So given two functions, so whenever they are intersecting, that's the solution point, right? So this is what we know. This is a line we know. If equal to 0 and draw this line. So how do you draw? So 2x plus 3y equal to 0, you draw this line then, right? So this is one way to find this solution. So another way is you take this 2 as like kind of some variable, 3 as some variable. So let's say some variable assigning to x, some variable assigning to b. So let's say if a equal to 2, b equal to 3, um, not a plus not a b individually. So you have to take a plus b equal to 2, then a minus b equal to 3. So I am unable to formulate it properly. How do we convert it into different variables instead of x and y? So something like this, you assign some a b new variable corresponding to x and y. A assigned is assigned to x and b assigned to y. Kind of if you now try to figure out what are the coefficients, coefficients will be now in the form of a and b, and this variable will get eliminated. Now we are solving in the using help of this a and b variables instead of x and y variable. So I'll share a proper slide for this. So the goal is we know, okay, if you minimize this under this constant, this is a solution, but we are unable to minimize because this constant is somehow infeasible for us to solve, right? So instead of now getting rid of this xy variable, how do we get some extra variables that will help us to kind of get the exact same solution? Okay, so that's the goal of this dual problem. So I'll share slides later. Maybe tonight I'll share the slides, go through that. So for now, just imagine there is a this whatever the problem statement we have is a primal solution. We have to convert it to some dual solution that will get rid of this x variable, right? So that we can get into this feasible region and we can solve this max min scenario. So primal was our initial optimization problem, minimize this f of x. This was infeasible because x was growing large in terms of dimensions, right? Now we want to get rid of this x to into some other variable. So now, so how do we get rid of this x? So this conversion is called the primal to dual conversion. So okay, so there are some okay, so if I try to solve this alone, this particularly minimization f of x, the constants are, let's say, some hx, the Lagrangian forces constant to be in a way. So there is another function that is again parameterizing x with this constant h of x is greater than less than equal to 0, and L of x is equal to 0. So these are some extra constant on the Lagrangian. So if your given constant is not in this form, let's say some constant is given, a transpose x is greater than 0, you can easily convert it into a transpose negative a transpose x less than 0. So always you have to given the constant, you have to convert them into this format. This is what Lagrangian tells us. Once you have converted into this format, now what will be the dual? So the primal formulation will be, instead of just minimizing this, you minimize something called Lagrangian equation. Lagrangian equation will be f of x plus lambda I into h of x plus some beta I into L of x. So this will be a Lagrangian formulation. So instead of just minimizing this under this constant, you merge this constant into the optimization problem. So now so why minimizing this is minimizing this, because there is some constant. So this is already negative, we know. This is already 0, we know. So this doesn't affect to the minimization problem. You can completely consider this to be 0. Now if we this we know is less than equal to 0, right? So this, if you know this is less than equal to 0, minimum value of like at what scenario this will let's consider if lambda is negative. So two possibilities: if lambda is negative, lambda is positive. If lambda is negative, what will happen? Negative into negative, it will grow high. This overall term will grow high. It will greater than equal to 0. Right? If it becomes greater than equal to 0, this overall term, then we will not achieve the actual minima, because this overall term will be higher than just f of x. Right? That's why we put a constant here. Lambda I has to be less than 0. So less than equal to 0. So under this constant lambda I less than equal to 0, beta I generally we don't put any restriction. There are different variations of Lagrangian. Somewhere they put restriction on beta I, but we don't require any restriction on beta I because Lix already is 0. So lambda I into hx, if we make it to kind of some negative value, then optimizing this will give us this minimization problem. So that's why this converting this minimization to this Lagrangian doesn't hamper our optimization problem. But in a way, it will help us to get rid of x. Again, how it will get rid of x? This is a very long formulation. So this is beyond your kind of course syllabus. I'll again give you the pointers. So what happens now? Converting this primal. This is again the primal, because we have the optimization problem in terms of x, right? So we have not gotten rid of x. Now converting this complete Lagrangian into something max min problem. Max of some variable, we'll see what is the variable. Max of some variable where x is not involved. So we're maximizing over some let's say some alpha beta. So what are these alpha beta? Alpha beta are this, not alpha beta, lambda beta. So lambda beta are these Lagrangian variables. So instead of optimizing over x, so here minimizing over x, right? So instead of optimizing over x, now we converted into a dual where we're optimizing over lambda and beta. So lambda beta are the Lagrangian variables. So they are feasible to solve for us. Okay. Any doubt? So this is at very high level. Again, I'll share a slide for your help. Just understand this is why we are converting primal to dual, and what will happen if you convert primal to dual. So we'll get rid of this x parameter. Okay. So for the problem, like optimization problem given to us, we know this is the minimization problem. These are the constraints. So how will we write the Lagrangian? So as I mentioned, we have to convert everything into in this format: hx less than equal to 0, lx equal to 0. So after converting, so we have already everything in the format written here. So if you see here, this we can multiply minus on both sides. This will become left hand side less than equal to right hand side. So that's what exactly we have done here. Multiplied the minus here, right? So now the kind of the primal solution is, this is our primal. Primal will be what was our original optimization, W transpose W by 2 plus summation of xi I, then plus lambda I into something plus beta I into something, right? So the lambda I beta I are these things. Okay, instead of lambda I beta I. So in the slides it is alpha I and mu I. Okay, so these are called the Lagrangian variables. So again, this is from some source. So they have taken constants on mu I, but this is not necessary. Only necessary constant for us is alpha I to be positive. So that the optimized solution for this will give us the optimized solution for this also. Okay, now if you we need to get three variables, like there are three variables here, w, b and xi. Again I mentioned I'm interchanging b and w0. So you have to kind of differentiate that whatever the primal we got with respect to w, b and xi. So if you differentiate like this is easy differentiation, you can work it out on your own. So if you differentiate, what is the optimal w you will get? Summation of alpha I, yi, xi. Then while like differentiating with respect to b, we'll get summation of alpha I, yi equal to 0. With respect to xi, we'll get this relation mu I plus alpha I equal to c.